Okay, so now we will start the third mini course number 3, which will be given by Rafael Potrie, and Rafael will speak about collapsed Anosov flows. Please, Rafael.
Hey, so thank you very much, and thanks for the opportunity of giving this mini course. And also, I will take the chance to wish Lorenzo a happy birthday and say that okay, besides we all know him and his good mood, I'd like to remark on his kindness, in particular towards young people, and which I received when I was starting, and so thank you very much. Okay, and the subject of the mini course I will give, so I plan to start quite slowly and to see where I can reach, but I already made a plan which is tentative, and the idea is to start by just discussing the motivations for studying partially hyperbolic systems, in particular in low dimensions, and give some very important examples. I think these examples are, again, so for the third time today about geodesic flow in negative curvature. So it also gives another point of view on the same, and I think that the same kind of ideas will also appear later. And then the goal I have is to discuss some more recent examples of partially hyperbolic systems in a very specific setting, and try to describe some of their properties that motivate the introduction of the class that we call the collapsed Anosov flows. And finally, to discuss a little bit about their properties and how to use them. Okay, so let me start by discussing some of the motivations of the subjects I'll discuss in this mini course. So the first motivation, and which is actually one of the things that motivates me the most, is to understand the link between the topology or the geometry of a phase space and the kind of dynamics it can admit. And so and the interplay between the topology and geometry and the dynamics is something it's very rich and allows to produce several kind of useful results in other settings. So this is kind of one of my main motivations, and this is the specific subject or framework where this mini course lies is in the context of classification of partially hyperbolic diffeomorphisms in dimension 3. Okay, and this is something that has to do with the fact that in low dimensions we have much more tools, topological tools, and also some they are good models to start understanding these systems. But the focus I want to give, in order to avoid entering into a lot of details about topology and geometry, which may be farther from a dynamical system school, is try to emphasize on the points of view that have to do with understanding dynamics of certain systems and how the class of systems that I will present can be attacked to understand their dynamical properties. And that, I think, is something that for these new classes of examples is really like open ground. There are many questions and there's place to play around a lot. And my main goal with this mini course is to present this class of examples, give some properties and give whoever is interested in to have a tool to play around and ask questions about dynamics, etc. Okay, so this is kind of the goal for the mini course. And so the class of systems I will try to understand is the class of systems, and right now I won't be in dimension 3. I will give some examples just to explain the kind of systems that belong to this class. And in the next lectures, I will enter a little bit more in the details of other constructions and in more specific situations in dimension 3. Okay, so a partially hyperbolic diffeomorphism is a diffeomorphism which preserves a splitting into three bundles. I will assume that they are non-trivial, so that there are variations of the definition, but this will be the context of these lectures. And the condition that they verify is that vectors in the stable bundle are uniformly contracted by the derivative. Vectors in the unstable bundle are uniformly expanded by the derivative, and the vectors in the center direction, so I'm taking unit vectors, have an intermediate behavior with respect to the other two. Okay, so this is a standard definition. The idea that one can take in mind is like you are able to put local charts around each point, and in a certain sense, the derivative preserves the coordinates of these local charts around each point. And this one tries to see to which extent this allows you to reduce the dimensions on the dynamics you are trying to understand. Okay, and later we will be way more restrictive and work in dimension 3, where all these three bundles will be exactly one-dimensional. And so then you can expect to use some at least basic facts about one-dimensional dynamics to understand the systems. Okay, so the first thing I wanted to do is, so why should we study partially hyperbolic diffeomorphisms? And there are many reasons. So in particular, one of the main reasons you want to understand this class is because it's an open class. Even though the definition is not obviously open, I will discuss in the next lecture why this is an open condition, and it already describes open sets of dynamics, and so you cannot ignore them, at least. And moreover, they appear very naturally in several contexts. And one of the contexts I want to focus on is in the context of algebraic examples, because it's an interesting class, and the fact that it's open, it tells you that whenever you have an algebraic example, you make a perturbation and you still have a partially hyperbolic system. And a lot of questions and results in partially hyperbolic dynamics involve understanding the dynamics of perturbation of algebraic examples. Okay, so what do I mean by an algebraic example? And so I will put in green, I will say the abstract things, but I will be thinking about two main examples for today. And after I explain the general setup, I will describe more precisely these two specific examples, which are the ones I want you to have in mind, because they will be the most important for the rest of the mini course. Okay, so you take a Lie group. A Lie group is a manifold with a group structure, and the examples you can have in mind are R3 as an abelian group. You can add vectors in R3, or PSL2R, which is the isometry space of the hyperbolic space, and can be identified with the unit tangent bundle of H2. Okay, so this is these are two classical examples which will be important for us, and you will consider a co-compact lattice on the Lie group. So the reason I will be assuming co-compact is because I'm working on closed manifolds, and there are many reasons for that, but the main reason is because it's easier. And I will restrict to that case. And for instance, in these examples you have here, so you can take C3 as a subgroup, discrete subgroup with compact quotient of the three-dimensional Euclidean space, which gives you the manifold we know as the three torus. Okay, and this is a drawing of a fundamental domain of this action. It's a cube, and you identify bottom with top and stuff. And in PSL2R, to construct co-compact lattices it's a little bit more challenging, but it's possible, and you can, for instance, decide to use important results such as uniformization theorem or whatever, and you know that you can make a geometric universal cover of a surface with constant negative curvature, and this will produce a discrete subgroup with compact quotient of PSL2R. Okay, so these are two examples, and in these examples we get the three torus, and with this example we get the unit tangent bundle of a surface of constant negative curvature. Then we will choose a Lie group automorphism. This means just a smooth map that preserves the group operations, but with the additional property that it preserves the lattice we are taking. So this means that it takes elements of the lattice into elements of the lattice. And in fact, this can be something very general, but we are thinking about exactly two cases. And in these two cases, so for R3, the set of automorphisms that preserve C3 are matrices with determinant 1 or -1. You can think of determinant 1, it's no problem. And these integer matrices have the properties of, since the determinant is 1, the inverse also has determinant 1, and so you get this property. And the idea is that this will induce something in the quotient too. Okay, and in PSL2R we are taking an even easier automorphism. We will consider the identity. Okay, it's very hard to find, as hard as impossible, to find an automorphism that preserves the lattice. And okay, and here I gave two examples of automorphisms of R3 preserving the integral lattices, which have a somewhat different behavior. Okay, so this one is a symmetric matrix, and the eigenvalues are, so the characteristic polynomial of this matrix is irreducible, and so it doesn't have rational eigenvalues. And this you can compute, you can put it on the computer, and it will show you that you have two eigenvalues which are larger than 1, they are different, and one smaller than 1 that are like this. And of course the eigenspaces are orthogonal because the matrix is symmetric. And another example, I did it on purpose so that it's not symmetric, so I put a 1 here, and it has one rational solution. The eigenvalue is exactly 1, and then 2 irrational, and then you have the 2, 1, 1, 1 map, which is classical. And this means the fact that you have a rational root, it means you have a rational eigenspace, and when you have a rational eigenspace, it will project to the torus as a foliation by circles. Okay, And this is another example to have in mind. Of course, there are many other examples. I won't tell how to describe all of them. And finally, we will consider some element of the Lie group and consider the left translation on the group here. Then after I continued writing this, and then I switched notation, and I'm sorry. So you can, there's some choice you need to make here. You will choose when the Lie group is not abelian, then it's not the same to act from the left than to act from the right. And so you will choose one side to act as isometries, and then the other side typically won't be acting as isometries. The good thing is that since we want some contraction and expansion on some vectors in the tangent space, we want to act in such a way that the action is not an isometry. So we need to act from that side. Okay. And finally, if you have all these givens, okay, the Lie group, a co-compact lattice, a group automorphism, and some left translation, you can define a diffeomorphism of the compact manifold, which is the group over the lattice. And so I'm acting on the right, so that acting on the right are isometries. And so now I can act on the left. And so the map F is F of xi gamma is H of phi of xi gamma. So since phi preserves gamma, this is well defined and gives you a diffeomorphism of F. You can compute the inverse, because phi has an inverse which also preserves this, and H, the left translation, also has an inverse. And the important thing about this thing is it's very homogeneous. So what you're doing is an automorphism of your group, which essentially looks the same everywhere, and a translation. And the translation also looks the same everywhere. So the derivative is constant, and you can compute it using Lie algebras or whatever. So if you are acting from one side, then the Lie algebra, you are translating it by right translation. So when you compute the derivative, you get the adjoint action of H composed with the derivative of the automorphism. And essentially, you have a very easy to verify criterion. If this matrix, which what's
the adjoint action?
So it's the derivative of conjugating by H in the identity. Okay, because essentially you are taking, say, I will compute this precisely in the case of PSL2R. So this I don't want to discuss Lie groups. So this is just something that if you know it, the point is this is a formula that allows you to compute the derivative of this map, this diffeomorphism at every point. By choosing the right coordinates, this derivative is constant. And of course, if this matrix has one eigenvalue, some eigenvalue larger than one, some eigenvalues equal to one, or different modulus of eigenvalues, then you will have a splitting, as in the partially hyperbolic splitting, and this diffeomorphism will be a partially hyperbolic system. Many homogeneous systems will be like that. A remark I'm making here is that the fact that the derivative is constant tells you that the determinant has to be one everywhere, because if you contract everywhere, then the compact manifold should be mapped inside. So the derivative has to be, the determinant has to be one, and so the map that you are defining is volume preserving. And then there are many ways to try to understand the dynamics of this volume preserving map, etc. Okay, so now, and what I will discuss is this construction in very specific examples. And so the first example won't answer Catherine's question, but the second one will. Okay. So the first example, maybe it's the one most of you know best. The second one probably too, but I wanted to give this example very precisely. And it's, you take a matrix with integer coefficients and determinant one. If you want to think about these two matrices it's okay. And the condition you are asking is that the eigenvalues are all of them are different. Okay, and so you will have one-dimensional eigenspaces, and if you define the FA to be FA of X, the class of A of X, as we said, since the matrix preserves the integral lattice, this is well defined in the quotient. Let me point out that in a more general setting, if we wanted to add something here, we could add here some vector B in R3, and that's also well defined. But in the translations in R3 are not very interesting because they are isometries. But you could do something affine here, but I will restrict to this case. So you can compute, and the inverse of FA is F of A inverse, which is also a matrix in SL3C. So if we identify the tangent space of the torus with R3 at every point, so with the identification being the point X comes from R3 as a projection, and its tangent space is canonically identified with the same R3 where it lives, and this identification is equivariant. So you can define this in the quotient, and the derivative of the automorphism is exactly the matrix A at every point. And so using this identification, we can define three eigendirections that are preserved by the derivative and verify the conditions of partial hyperbolism. Okay, so one relevant thing to say that through every X in R3, the affine space, which corresponds to even though it lives in the tangent space, since it's a vector space, you can project it to the manifold, and this projects to an immersed submanifold, which is everywhere tangent to E sigma. If the eigenspace is rational, then the projections are circles, because the solution, so the eigenspace is generated by a rational subspace, and then the immersion has circles. But if the eigenspace is irrational, then they are totally irrational, or at least. So if the center, it only depends on the center, because the only rational solutions you can have are plus or minus one. And so since we are assuming that the three eigenvalues are real and different, you can only have one rational one. And in this case, you get circles. And if the center one is not rational, then all directions are project to dense lines in the torus T3. Okay. This is something you can see. And if you have one, then it's more complicated, because the eigenspace associated to the eigenvalue larger than one is dense in a submanifold of T3, which is another torus. Okay, so this is what I wanted to explain about the examples in T3. In the mini course, I won't be concentrating on these examples, but these are very important examples of partially hyperbolic systems, and a lot of work has been done in trying to understand the dynamics of perturbations of these maps. Okay, so and as I said at the beginning, what I try to do in this mini course is to give another class of examples where the dynamics has not been studied and could be studied but here you will have a source of questions to make. Okay. And so let me give some examples in the unit tangent bundle of a surface of a constant negative curvature. So we are taking as I said, this PSL2R, which you can identify with the isometries of H2, and the isometries is this identification is made via the action in H2. So H2 is the upper half model, and so if you have a 2x2 matrix with the determinant 1 up to identifying identity and minus identity, you get a Medius transformation of H2, which preserves H2. And you can check that it preserves this Riemannian metric, and you can check its constant negative. So the homogeneity of this metric tells you that the curvature is constant. So the only thing you need to check is that this constant is negative, and then I'm not sure if this is constant -1, but it's constant minus something. Okay, so let me explain that. So why, if you check that Medius transformation preserve this metric, and to do that, one way is to decompose Medius transformation into simple transformations where you can make the computation directly. Then you need to see that you can go from any point to any point using this Medius transformation. So the way to do this is, let's fix a point and a vector in T1 of H2. So it's a point in H2, and then I need to choose a vector which has norm 1 with respect to this metric. So since the imaginary part here is 1, I just need to take a vector which is of size 1. So I'm taking the vertical vector, and so this defines a line which goes through 0, I, and infinity. This is well defined. And then if I fix a point and a vector here, I can draw the circle which is orthogonal to the real axis through that point and that vector. And to map this point and this vector to here, I just need to fix the Medius transformation that maps 0 to 0 to this point, infinity to this point, and then I still have one parameter to fix that I maps to B. Okay, and then since Medius transformation preserves the lines and circles and angles and stuff, you get this. Okay, and this is unique. This is also something that follows from the properties of Medius transformation. So this is the identification I claimed before between PSL2R and the unit tangent bundle of H2. So here we are identifying the identity with this point and this vector because we are acting on it. But then, since we are acting on the vector here, the isometries we are taking, so we are moving the action by isometries is action on the left, which is exactly the opposite thing I said at the beginning. Okay, and I'm sorry for that, but I just noticed. So okay, and to parameterize this thing, which is a geodesic, and you can check it's a geodesic, you just need to multiply I with this vector by this matrix, and this is exactly the geodesic parameterized by arc length. It's gamma of t. It goes like this. So if you want to look at the geodesic through this point, what you need to do is you fix the Medius transformation that maps this point to here, and then this is acting on the left. So you need to put the geodesic, the parameterization of the geodesic, on the right. Okay, so this matrix, let's call this matrix, say, gamma of t, verifies that gamma of t of the point I and vector I goes to the point gamma of t here. Okay, this is what we are checking. So this is a way to see that. So that therefore exactly the geodesic flow, which I won't define. You have already some class saying this. You can check in this concrete example of constant negative curvature is the action on the right by this one parameter subgroup of PSL2R. Okay, so now if you fix a co-compact discrete subgroup of PSL2R, which as we said is the choice for instance, is the choice of a compact surface of constant negative curvature. This produces a way to construct this group. Then you can act on the left by isometries of H2, and then you get that the unit tangent bundle is exactly this quotient. Okay, it's the PSL2R mod by the action of this compact subgroup by isometries. And so this produces, since we are acting by isometries, this produces a manifold, which is compact, and endowed with a metric, which is the Riemannian metric will take. Okay, this is kind of an example. Another way to construct these examples is you can do some symmetric ones by checking that as you move to infinity, if you take like an octagon here, it's very close to Euclidean, so the angles are too large. But then when you move up to infinity, you get angles equal to 0 in an ideal octagon. So in the middle, you will find a place where the angles are exactly the pi over 4, so that the action by these transformations will produce a discrete subgroup whose quotient is the surface. Okay, so as we said, and this is the thing. So the geodesic flow, now if you have a compact surface with constant negative curvature, has also a geometric interpretation, which is you take a point and a vector and you flow around the geodesic with that initial condition. It's a differential equation, and so you get a solution. And this solution, what we were saying is that if you write the geodesic flow as this, so if you start with a point and a vector, then you take the geodesic with these initial conditions through that point at time t, then if the point PV is identified with this class in the quotient for some G in PSL2R, then doing the geodesic flow is exactly the same as multiplying by the matrix AT. And so now we have a flow, a dynamical system on the unit tangent bundle of a surface. And now we have a compact manifold. So now I want to check that this dynamical system is partially hyperbolic. Okay, and this one is, for instance, taking A1. But any time will work. So the claim is that for every t different from 0, this diffeomorphism of PSL2R is partially hyperbolic. And so essentially what I will be doing is computing. So if you know Lie algebras, what I will be doing right now is computing the adjoint action of AT on the Lie algebra. And this will be exactly the computation I'm making. But I will do it with a different point of view, but it's exactly the same. And so if you determine these two, these are other, so the reason the computation will be simple is because I know the answer, so I know where to compute. But it's not so hard. But so these two are one parameter subgroups of PSL2R, and they have a very nice property of commutation with respect to the geodesic flow, which is this one. So this I wrote. You can check this computation. It's very simple and tells you that if you do A minus T US AT, you get U e to the t s, and a similar thing goes for the lower triangular matrices. Okay, but you get a minus here. So and what does this tell us? So you take any G in PSL2R. So I want to compute the derivative. So if I want to compute the derivative along the flow direction, it's very easy. Okay, because it's just conjugating by AT, and this doesn't do anything. So the derivative along the flow direction is 1. But then this is a 3-dimensional space, so I need 2 other vectors on which to compute the derivative. And I claim these properties tell me that these vectors give me eigenspaces. And the computation is as follows. So you take any xi and PSL2R. So this is a curve in T1S, gamma xi US. And if I apply the geodesic flow at time t to this curve, I get this curve. Okay, I apply it because I'm multiplying on the right. I get AT US xi gamma. And then I apply this commutation relation, and I get E U E minus TS. So it means that if so this flow maps xi gamma xi into gamma xi AT, and it maps this parameterized curve into this parameterized curve. So it's contracting the length of the curve by a factor of exponential minus t. So essentially what I'm saying is, if I take this vector field on the surface, which is the derivative as s equal to 0 of this curve, this belongs to the tangent space of the unit tangent bundle of the surface. We compute the derivative, which means I take the derivative of this other curve, and I get e to the minus t times the vector if I look standing on this particular point. And similarly, you can do the same with defining bu as the derivative of the other one thing, and you get e to the t, which is consistent. So if you take the basis given by bs, bu, and the tangents direction to the flow orbits, you get a basis at every point which is preserved, and on which here you are multiplying by 1, here you are multiplying by e to the t, and here you are multiplying by e to the minus t. So this is very consistent with the fact that we mentioned that the determinant is 1. Okay, so what we contract, we expand, and this forms a basis of this and gives us a partially hyperbolic basis. So at every point we put this basis, and this is preserved by phi t, and has the properties of partial hyperbolicity. So so these 2 drawings will appear a lot of times. So and sometimes we'll draw it on the upper half plane, and sometimes on the disk. And in general, you use the upper half plane when you are trying to fix your attention on a geodesic ray. So this is the most convenient way, because you have your favorite point in this model is infinity, is a point at the boundary, and we will use this model when we want to fix our attention on a point inside the space. And these are drawings about how the flow lines behave. Okay, so since I have some minutes, what I will do is try to describe in a little bit more detail what I will do. No, I don't have much more minutes. I have 1 more minute. So I will stop here.
Actually, you have 6 minutes. We started 11:15.
Okay, I thought it was 40. Sorry. So I will say a couple of words about at least the next time. Okay. So the idea is, okay. So we'll look at we are looking at partially hyperbolic diffuse on 3 manifolds. Okay, we just made some examples, algebraic examples, and so how to get new examples. So the first way to make new examples is to make small C1 perturbations. And small C1 perturbations, thanks to some like structural stability of partially hyperbolic systems known as Hirsch-Schub stability, will tell us that these perturbations are not very different topologically. Okay, they can be very different dynamically. So in fact, this has been object of many works, and in partial hyperbolicity, which is try to see which kind of dynamical properties you can extend to a neighborhood of some algebraic example, taking into account that Hirsch-Schub tell you that the topological structure is not changing. And so, in the next lecture, what I will explain is how to do one can make perturbations which are very big in C0, but still small in C1. And this doesn't make sense because the C1 norm includes the C0 norm, but we will make this to have some sense, and using this we'll construct new examples and try to see, so the goal of the lecture is try to see which is the class of the topological class of these new examples to be able to have the starting point to ask the dynamical question. So next time I will start with the geodesic flow in a closed surface of negative curvature and try to make big C0 perturbations which are small C1, so to produce new partially hyperbolic systems, but which are very different from the one we started with. Okay, and this will motivate the class of the title of the lectures. Okay, so that's it. Thank you.
Okay, thank you, Rafael. Do you have questions or comments? I believe it was so clear that nobody has any doubts.
Or anyone is shy to ask. You don't know.
Or maybe we are tired.
Maybe also this. Okay.
Yeah, let me recall the students that you should ask questions. Okay, there is no problem. The school is for this. So, do you want to ask a question, Zaza?
No, just a suggestion, but after, when you close the...
Okay. So let's thank Rafael
I have
again.
a question. It may be,
okay,
it may be silly, but when you said the lambda C was equal to 1 or minus 1, we have that lambda U and lambda S are irrational. This is for any dimension or any dimension 3, or just for dimension 3?
Yeah, it's a good question, and I said it very fast, and it's only in dimension 3, and it's very specific to this. So the point is that the characteristic polynomial of A is a polynomial with integer coefficients, and so there is and the determinant is 1. Okay, so you get the rational root theorem tells you the only rational roots that are possible are 1 and -1, and then it's you take down, and then you get an irreducible polynomial of degree 2, and so you have to have conjugate, like Galois conjugate solutions or whatever. But it's an algebraic property. It's not really relevant. I'm just stating this as a fact. It doesn't have to be understood. It's just a fact that in principle other things could happen for automorphism, but there are some algebraic restrictions, and that's it.
Okay, thank you.
Okay, so let's thank Rafael again.